So the next integration technique that we want to look at is one called integration by parts. So this is kind of building off of the substitution, which if you remember was a kind of an answer for the chain rule of derivatives, right? Like how we would undo the chain rule. So this one's kind of an answer for the product rule. So if we remember the product rule, so let's say if we had f of x times g of x, and we take the derivative of that, we would get f prime of x g of x plus f of x g prime of x. Okay. So if we were to integrate both sides of this, which by the way is something that you can do, okay, I don't think we've ever really seen that before, but that's a very common thing to do, is to integrate both sides here. Then what we would get, let's go ahead and I'll just write it in the middle here. And remember, when we're integrating a sum, right, we can just integrate both parts of the sum. And I'm going to squeeze a dx in here as well, because we are integrating with respect to x, which is the only real variable we even have defined here. Okay, then when we integrate this part, we're just integrating the derivative, so we're just going to get back to the original. Okay, f of x times g of x. And then this is going to be equal to, well, we can't really say what this is, right? So we'll just leave it like this, and then we'll use this to make our formula. And then same with this part. So the only thing that we can definitively say is that the left side right here becomes f of x g of x times g of x, that is. Now we're basically going to rearrange this so that we have a formula for this part right here, which will allow us to solve for integrals that are of this form, which is something that we're missing. So we're gonna basically we'll just subtract this part from both sides, this middle part here, the f prime times g of x, but I'll rewrite it to put the part that we want on the left. Okay, so we have the integral of f of x times g prime of x dx is equal to f of x times g of x minus the integral of f prime of x times g of x dx. Okay. So relating this to substitution makes it a little bit easier to see exactly how we would implement it. So if we let u be equal to f of x, okay, and v be equal to g of x. Okay, so we have two functions. So we want to introduce two variables. We're making two substitutions here. So this will imply that du is equal to f prime of x dx, and dv is equal to g prime of x dx. Then we can go ahead and make some of these substitutions into the formula here. Okay. So this tells us that the integral of u dv for this first one, okay, and I know these letters, they can often kind of blend together depending on your handwriting, so just you want to be careful if you're using these look very similar, maybe use different letters, but these are the ones that are commonly used for this process. So anyway, so u times dv, this part right here is just u times v, and then minus the integral of, well, we could rearrange this a little bit and we see g of x is v, and then f prime times dx. We don't want to separate the primes and the dx's, right, because they're together in that formula here, so we don't want to do anything too overly complicated. So f prime of dx will be du. Okay. So this gives us a formula to work with here. This is the integration by parts formula. So how do we actually go about implementing it then? So we need something that wouldn't work with a normal substitution, right? So we would need basically to something that we could kind of divide into two parts. Okay. So let's go ahead and try one, that wouldn't work with any method that we've seen so far. And we'll see exactly how we can implement this formula. So we have the integral of x times e to the 2x dx. Okay. So first of all, why wouldn't this work with our other integration formulas that we have up to this point? Well, if we tried to do a substitution, like if we let u equal to e to the 2x, for example, then du would be equal to 2e to the 2x. And there's really no, good way to rewrite this formula, right? Times dx. So we would end up with u, but there's no good way to substitute out that x for anything, right? You might think to let u, maybe make the substitution of u equals 2x, which would maybe get you a little closer, but unfortunately when you take the derivative here, you only get 2 dx, right? That might be a good technique for a different problem. If this was like x squared, for example, that would be a good thing to do. But in this case, that's not really going to work. So what we want to do instead is this integration by parts. So basically, we have two unrelated things, right? One of the parts is not the derivative of the other part. So we kind of need to make two substitutions because we have these two unrelated things. So then the tricky part comes in, okay, what are we going to let u equal to? And notice the substitution we're doing in this formula, actually. We're trying to solve things of the type u dv. So we're going to make a substitution of letting one of the parts equal to u, and then the other part equal to dv. Okay, so that's an important distinction as well. Okay, so we're not letting one part be u and letting one part be v. We're letting one part be u and one part be dv. So that means we're going to find what v is by taking the antiderivative of dv. Okay, so first of all, just think for a second, which parts of these should be which, right? So one of them you're going to take the derivative of, the other one you're going to take the integral of. And we want to make this simpler, right? We don't want it to become more complicated, okay? So if you just think about it for a minute, hopefully you would see, okay, if I take the derivative of e to the 2x, it's going to be basically the same thing. And if I take the integral of e to the 2x, it's going to be basically the same thing because it's its own derivative, right? Whereas, so that one, it doesn't really matter which one it goes into. It's going to be just as simple either way. With the x, if we let u equal x, when we take the derivative, we just get 1, right? 1 times dx. So that's very simple. If we let dv equal to x, that means v would be equal to x squared over 2, right? So this makes it more complicated. So that's probably something we don't want to do. So we'll keep it simple and we'll let u equal x, okay? So then du is equal to just dx, 1 times dx. Now, we're going to take dv to be e to the 2x dx, okay? So essentially, right, we're letting this part be u, this part be dv. So then v is the antiderivative of this, okay? Which, you actually would technically need to do a substitution to solve this one. This is one that kind of comes up a lot, so you get kind of used to it. But you would, if you want to introduce another variable, maybe use like y or something. So maybe you just do it off to the side, like you let y equal 2x, and then dy equal 2 dx. Okay. So then you have the integral of, you divide both sides by 2 here. So you have 1/2 e to the y dy. So you get 1/2 e to the y, which is going to be e to the 2x when you put it back in. Okay. So this is a good general formula to kind of be aware of. So you don't have to do the substitution every time. Just if you have e to like integral of e to the kx dx is going to be 1 over k e to the kx, right? Okay, so just a little bit of an aside there since it came up. So anyway, so this is going to be 1/2 e to the 2x. So we have x, we have du, we have dv, we have v. So now we can go ahead and just plug everything into this formula here. Okay. So the formula is that the integral of u dv, okay, so u is x, dv is e to the 2x dx, right? So this is just our original. U times v, x times 1/2 e to the 2x minus the integral of v du. Okay, so v is 1/2. Put that on the outside, e to the 2x. And then du is just dx. Okay. So we still have an integral to evaluate, but this is a lot simpler now, right? We actually just did this integral. So this is no issue for us. So sometimes you might have to do an extra step. Sometimes you might even need to integrate by parts again. But in general, you should kind of see that it's leading you to a solution. So 1/2 e to the x e to the 2x minus this part's going to be 1/2 e to the 2x as we just saw. So this is going to be 1/4 e to the 2x. And then if you want to be a stickler about it, you can put a plus c right there. Okay. So this is how we would implement the formula. We pick a u, a part of it that is going to be differentiated in the substitution. We pick a v, or a dv rather, a part that's going to be anti-differentiated, and then we can stick to the formula for the rest of the part. Okay. All right, so we'll do some more examples here because there's a lot of tricks that can come up in this. Like I said, you might end up having to integrate by parts twice. Sometimes it starts cycling, like you end up back at like what you originally had. So we'll look at ones like that. So I'll do a separate video where we go over just some examples. I'll just do one more in this one because this is an important one. You might have been wondering, maybe not, but maybe you've been wondering, how do you evaluate the antiderivative of natural log of x? Okay, this is a very common function, and it was kind of suspiciously left out of the antiderivative video. So why? Well, the reason is because you actually, you really need integration by parts in order to evaluate it properly. And when you're looking at this now, that might be kind of strange. That maybe is unexpected, because if you look at this, you might be thinking, well, why would you need integration by parts for this when there's not even two parts, right? So this is another thing that can come up sometimes, is that even if there's not actually two parts, integration by parts can still help you out quite a bit with the problem. So here we're going to let, well, we don't really have a choice here other than to let ln of x be u, right? Because we don't know the antiderivative of it. So then we're just going to let dv equal to dx, right? It's like that there's like a 1 times dx here. Okay. So then du is going to be equal to 1 over x dx. And then v is going to be equal to x. Okay. So it's like we're taking the antiderivative of 1, which would just be x. And then we'll follow the formula from there. Okay, so we're going to do the integral of the natural log of x dx is equal to u times v, so x times the natural log of x, minus v du. And you can start to see where this is going to fall into place. right? This is an easy cancellation here. So now we just have the integral of 1, which we just saw as x. So overall, this is going to be x natural log of x minus x. Sometimes you'll see this written as x natural log of x minus 1, just with the x factored out. Okay, but either way, this is how we would evaluate the natural log of x.